Okay, then last but not least, VeriEQL, bounded equivalence verification for complex SQL queries with integrity constraints, presented by Pinhan Zhao.
Hello everyone, I'm Pinhan, and today I'm going to present our work, VeriEQL, bounded equivalence verification for complex SQL queries with integrity constraint. This is a joint work with Yang He, Xinyu Wang, and Yuepeng Wang from Simon Fraser University and the University of Michigan. Let's begin by discussing why the task of checking equivalence for SQL query is important in today's data-driven world. The database management system and frameworks like MySQL and Calcite often rely on rewriting to optimize a slow query to a faster one. And we want to ensure that the rewritten query is semantically equivalent to the original one with formal guarantees. And in case of non-equivalence, we want to provide a counterexample to help the developer fix the incorrect rewrite. And checking equivalence is also useful for automated grading, such as LeetCode. And in this case, we want to automatically verify if a user solution is correct against a ground truth query and provide a counterexample as feedback to the user to illustrate why the query is wrong, if it is wrong. So let's consider a simple example. In this example, I will illustrate how a query that solves a real-world problem looks like. Suppose we have a database with two tables. We have table customers, which contains customers' information, and we also have an orders table, which tracks which customer has bought which product. And there are also integrity constraints associated with the schema. Specifically, customer ID is a primary key of the customers table, and order ID is a primary key of the orders table, which means that these attributes must have a unique and non-empty values. And the customer ID is a foreign key of the orders table, which restricts that each customer that bought a product must associate with an existing record in the customers table. And given this database, we are asked to write a query to find the customers who bought both product A and B but did not buy the product C before. So in this case, a desired output will be like this. Specifically, there's one row in the output table that the customer ID is 1 and customer name is Alice, who is the only customer who bought both A and B but did not buy the product C. And here we have a query that a developer may write to solve this task. It's fairly complex, so let me walk you through it in the next couple slides. Intuitively, the query uses a select from where structure to retrieve all records from the customers table that satisfy the given predicate. And in this case, we want to know each customer has bought product A, B, and C before. And to achieve this, we need to write 3 subqueries. The first subquery identifies all customers who bought product A before. And we use an in expressions to check if each customer is in the subset of those who bought A. And similarly, the second query identifies those who bought product B before. And the third query ensures that we exclude any customer who bought product C. And finally, the query returns all records that satisfy the conditions. As we can see, the query is fairly complex. But in the real world, a user may write even more complex queries. And it is often very challenging to verify a pair of 2 queries like this. So in this work, we aim to solve the problems of checking equivalence of real-world SQL queries. And to do this, we conduct a thorough study of over 24,000 query pairs. So let's see how these queries look like. Firstly, real-world queries often use different kinds of integrity constraints, like primary key, foreign key, not null, and many others. There are more than 95% of queries in our benchmark require consideration of integrity constraint. And there are more than 73 benchmarks uses the aggregate functions, like average, max, and mean, And there are 66% of queries use group by. These features are very important when writing the analytical queries. And there are also more than 20% of the queries use the order by operation, which is necessary to sort the query result. And the challenges that make the task of checking equivalence difficult can be broken down into 3 key issues. Firstly, prior work are very limited in handling an expressive set of SQL queries. Existing approaches like how SQL and UDP convert SQL queries into an algebraic structures. However, this intermediate representation often lacks in expressiveness needed to accommodate an complex SQL syntax. Secondly, it is important to account for rich interior constraints commonly used in real-world queries. And the third important feature to support is list semantics. Specifically, list semantics treat tables as lists and preserve the ordering of tuples. This is necessary to support the order by operation. However, prior work does not support list semantics and therefore cannot handle queries that involve an order by operation. Due to these limitations, prior work collectively support less than 2% of our benchmarks. So we want to address these challenges. To bridge the gap, firstly, we formalize the semantics for a large subset of SQL, reflecting the rich features used in real-world queries. Building upon this foundation, we develop a verification approach, VeriEQL, that is very standard but meets 3 key criteria. It supports an expressive SQL syntax to handle complex SQL queries. It supports rich entirety constraint, and it supports checking equivalence under list semantics to account for ordered results. This approach would allow us to tackle the full spectrum of SQL equivalence verification challenges identified in our benchmarks. And in the rest of my talk, I'm going to expand on our formal semantics and our verification approach, VeriEQL. So our formalization covers a rich subset of SQL operators, reflecting the rich features used in real-world queries. For example, we support the fundamental select, project, and join operators, as well as the group by and order by. We can also handle complex expressions like aggregate functions and case expressions. Like standard SQL, we also model our SQL semantics use 3-value logic. Specifically, a special non-value may be used to denote an unknown information. And to switch between the bag and list semantics, we denote our semantics in functional programs with higher order combinators that operate over lists. We interpret tables using lists when necessary to support the order by operation, which requires preserving the ordering of tuples. And we treat the table as bags when the queries don't involve an order by operation. So now let me introduce our approach, VeriEQL, to solve the equivalence checking problem. VeriEQL takes a pair of 2 queries as input along with a schema and a set of interior constraints. And then it will build a symbolic database. Here, a symbolic database is a finite input space that considers all possible input tables with number of rows up to a certain size. But the value of the cells are unbounded. And then VeriEQL will symbolically execute 2 queries on the symbolic database and produce their symbolic outputs respectively. And we'll then ask an SMT solver to determine, given the symbolic database, whether it's possible that 2 queries will produce the different outputs. And if this condition is unsatisfiable, then 2 queries are bounded equivalent, which means that 2 queries will always produce the same output on all possible input tables up to a certain size. And if the condition is satisfiable, then we found a counterexample that can make two queries produce different outputs. Now, let's walk through a simple writing example to illustrate how VeriEQL works. Consider this simple schema with an employee table with two columns, ID and age. And there is also an entire constraint that the ID column is a primary key, which means the value of the ID must be unique and cannot be empty. And let's look at the two queries we want to compare. Query 1 selects the ID from the employee table where the age is strictly greater than 30. And query 2, on the other hand, selects the ID from the table where age is greater than or equal to 30. The queries look very similar, but are semantically non-equivalent and can produce different outputs. And VeriEQL will begin by encoding the entire constraint. And in this case, we want to encode a primary constraint on the ID column. To represent this, we'll first create a symbolic database. And for our example, let's consider a bound of 2, which means we'll consider all possible input tables with up to 2 rows. And the entire constraint is encoded as a formula phi c, which restricts that the value of the ID column cannot be null and are distinct from each other. This encoding makes sure that VeriEQL will consider and reason about all valid database instances that conform to the given entire constraint. And then VeriEQL will encode two queries executing on the symbolic database. And we'll first create a symbolic table R1 to represent the output of query Q1 with two fresh symbolic tuples. And then we'll create a formula phi1 to encode the query Q1. And our idea is to use an uninterpreted function called deleted to denote whether a symbolic tuple exists or not in the table. And then we'll first encode the var class. Intuitively, if a tuple has age greater than 30, then the tuple is preserved in the output table. And then we project the ID column by copying the values. Otherwise, if the tuple has age less than or equal to 30, then the tuple is deleted in the output table. Similarly, we can create a formula phi2 to encode the query Q2. And finally, we'll construct an equivalence condition VeriEQ that states the outputs of two queries should have the same size and contain the same tuples with the same multiplicities, which basically means that the two queries are semantics equivalent under the back semantics. And more specifically, it means two multisets should contain the exactly same elements. And with all the pieces in place, we can now check for equivalence by solving this formula above. And in this case, VeriEQL will find a counterexample that can make two queries produce different outputs. Specifically, there's one row in the table where age is exactly 30. This row will be included in the output of query 2, but not query 1. We evaluate VeriEQL. To evaluate VeriEQL on solving real-world tasks, we use 3 different benchmark suites. The first and largest is from LeetCode with 23994 query pairs. And each benchmark is a pair of 2 queries of a user-submitted query and a ground truth query. And the second benchmark is Apache Calcite with 397 benchmarks. And each benchmark is a test case that a slow query is rewrite to a faster one via rules. And we also take another 64 benchmarks from prior literature. And we compare VeriEQL against several existing approaches. We included bounded verifiers like COSAT and QEX. And we also compare VeriEQL against full-fledged verifiers like SPAS and HotSQL. Additionally, we included testing approaches, Xdata, and data filler. So the evaluation result shows several key points about VeriEQL's performance. Firstly, it supports over 75% of our benchmarks, significantly better than all other tools we compare it to. Also, VeriEQL is very good at identifying non-equivalent query pairs. And the counterexamples identified by VeriEQL help us find serious bugs and contribute to real-world systems. Firstly, VeriEQL identified 4 non-equivalent rewrite rules in Apache Calcite, which rewrite a query to a semantically different one. We reported these issues to Calcite maintainers who confirmed these issues. This shows that even in a well-maintained and extensively tested system like Calcite, VeriEQL is able to uncover very tricky bugs that escaped existing testing processes. And VeriEQL also identified a serious MySQL bug. During our evaluation, we found 2 counterexamples produce the same output when executed on MySQL, which are supposed to produce different outputs. So we manually inspected the counterexample and the queries and found it is because the execution result of MySQL is incorrect. So we reported this issue to MySQL team, who confirmed and classified this issue with serious severity. Additionally, VeriEQL also identified more than 3,500 counterexamples for LeetCode benchmarks, which suggests that many user-submitted queries that are accepted by LeetCode may be actually incorrect. We filled missing test cases report for several problems and provide the counterexamples identified by VeriEQL, which then help LeetCode augment their existing text suites. And VeriEQL is also open source, so please definitely check it out. And this is the end of my talk. Thank you for your attention.
We have time for a few questions. Please step up to the microphone.
So thank you for your talk. I enjoyed it a lot. I think one of the major aspects to your work is that you formalize the semantics via, SMT encoding for a large subset of SQL. And I guess that, this may have, more use cases beyond, verifying that 2 queries are equivalent. So have you considered any directions for future work?
Yeah, that's an extremely good question. So actually, we are working on another project that applies this encoding to solve more problems in different domains. Yeah, that's our future work, indeed.
Yes, so looking forward to that, and thank you.
Thank you so much.
I was sort of thinking along the same lines. So maybe wouldn't another interesting case perhaps be a situation where one query produces strictly fewer results than another query? Would that potentially be of interest in some cases?
You mean like enforce a query's result must be?
So inclusion of a set of results in another set of results.
Yeah, that could be a potential application of this. Yeah, and I think our encoding should be applicable to this application.
Time for one more question. So if I understood correctly, you are bounding the tables when you're looking for potential counterexamples. In the all the properties that all of the equivalences that you were able to disprove, is there a sort of minimum depth or max or general intuition that you got about how large your counterexamples generally will need to be?
So I believe the small scope hypothesis is applicable to our domain. So many counterexamples identified by VeriEQL is indeed very small, like 2 or 3 rows in the table. And there is a statistic in our paper, and we can catch on this. offline.
Got it. Thank
Yeah.
you.
Okay, let's thank Pinhan again.